I want to tie together a lot of the things we've talked about and also illustrate the great power of some of these concepts beyond the specific things we've done with this last talk, where I've broken out a lot of the things that used to be rolled in and embedded in previous versions and deserve to really be spoken about at a high level here. So the first one of which is that we've looked at some building blocks right here, fully connected layers and convolutional layers that have been very powerful and very useful. But there are other layers also built on the same techniques, but it's only when we build these up into big pieces that they gain all their power. So let's look at a couple of those layers here. And although the list is long, if you go to Wikipedia or something, or just look at what's in TensorFlow for layers, in reality, you know, there's a long tail that really the top 6 or 7 are almost everything that's going on in successful practical networks. Not to say that some of these other ones won't become important someday. Certainly 5 years from now, there'll be some other layers that people didn't think were interesting that are very popular and useful. But at the moment, you know, there's really only a half a dozen layers that are used to build. Look at a couple of these other layers that we didn't quite get to, but are similar to what we're doing. As a matter of fact, some of them are just trivial modifications in what we're doing. I mentioned to you that vanishing gradients are an issue for a long time, a very, very difficult issue. And yet deeper networks can be more powerful. We'll see a few very deep networks that are popular and have been famous for what they've been able to do. So how do we kind of deal with this since we want these deep networks? Well, one very successful method is to just are called residual networks. And that's just doing some feed forward. It's very crude sounding, but yet effective technique where we say, okay, what if we just take some of the input and just feed it forward into the next layer? I mean, that sounds crude and maybe like it's disruptive, but yet it works very well. It's been effective for doing layers up to 1,000 these days. I've seen some networks that are over 1,000 do useful stuff, which is unthinkable without this kind of approach. And as a matter of fact, that's how AlphaGo Zero, which was the first superhuman Go machine, at the game of Go, it was 40 residual layers, and that was only made possible because of this kind of residual feed forward. And okay, is it really as crude as I'm just saying, feed forward? Well, the answer is yes. Here is what the kind of thing you can do. As I was saying, residual networks are really as simple and effective as feed forwarding some stuff like this. These are some TensorFlow lines right here that do exactly that. It takes X, the input, into the convolutional layer, and also feeds it beyond it into the next layer, Z, where we just want to feed Z into the next layer, and we're just adding X and Y, the output of this layer. So this is very trivial to do, very powerful. But haven't all of our networks been built strictly as these sequential layers in our, if we go and look at our code, we just said sequential and just add a bunch of layers inside of that sequential command saying make these sequential layers. Yeah, indeed, but it's very easy to use the functional API, which instead allows us to make networks that branch in different ways and do all kinds of funny stuff. So there's an MNIST example of using that. It's very obvious what it's doing. It's very simple to use. And so if you see more complicated architectures where the networks are branching out into pieces and doing different things, TensorFlow makes it very easy to do that. In our case, though, with residual layer, which we're talking about here, you can see MNIST with a 15-layer residual network. And it's kind of not the most effective approach, but it illustrates how easy it is to do residual networks, where it is more important and effective, like if you're going to do AlphaGo Zero. So it's pretty straightforward. Now, if feed forward is useful, it might occur to you that feedback is useful. Indeed, feedback is the principle of an incredibly important technique, recurrent networks, which allows us to start to capture some context in what we're doing. So far, everything we've done doesn't really involve context. It's just a single image at a point in time. We just look at a digit and say, what's the digit? We don't concern ourselves with surrounding digits or previous digits or whatever, and yet that's incredibly useful, important information if we're actually trying to recognize text or words or whatever. A very good example of this, exaggerated one, is this paragraph right here, which the vast majority of people manage to read just fine, even though it's incredibly juxtaposed text, right? So how does your brain do this? It clearly understands context to a great degree, right? Your brain is able to, for most people, fairly effortlessly understand this because of the context. And so here's maybe a more simplified example right here. If we've got something like this, the dog chased the cat up the tree. Well, I just read a cat. I know that's cat, right? Even though the A, if we just cut out the A, it's hard to read, but it's obvious to me that it's cat from its context, the surrounding letters and the surrounding words, certainly. So it's very easy from context to greatly improve your interpretation. that brings along the idea that we're kind of we're remembering some recent things that we saw here. And if it seems like memory, well, let's go ahead and absolutely just make some outright memory for our neurons ourselves. And that's where long short-term memories come from. And this is an idea first proposed in the late 90s by a couple of other giants in the field, but it's taken on many variant sets. As a matter of fact, I find people new to the field are most often confused because they hear about LSTMs and they know it's a good and powerful idea. They see it used a lot, and they'll go and read an explanation of LSTMs that have very specific mechanics. They say, okay, this is how the forget gate works, and this is how this works, implying like this is the way LSTMs are always done. And then they get confused because they go and look at another model and it seems to be slightly different. The reality is there are many variants of LSTMs. So if you just read Wikipedia article or whatever, and it misleadingly suggests to you that there's one LSTM, that's not true. A lot of options here. As a matter of fact, a good introduction to it is a paper, LSTM, a search space odyssey, that gives you an idea of how many variations there are. They all have the same idea, though, that we want to retain some information in the cell so we can better understand context. Keras has LSTMs built in, very simple layers, make it very easy to use. You'll notice there are a lot of options for that layer, reflecting the fact that there are a lot of variations of this, and it can deal with that. There's even an MNIST version of this, which I think is kind of very much overkill because this kind of approach isn't particularly necessary for looking at a single image. However, it's very useful for context, and I think a simple, small network, which shows you that in a very powerful way, is this example here, which uses it to predict the next frame of an artificially generated movie, which has some moving squares. So it actually is starting to recognize the trajectory of squares and remember things. So anyway, I think this is a better example. But these are widely used now in a lot of different architectures where context is important. And you can see how context can be used even more powerfully here, where we might have bidirectional LSTMs. These show up a lot in natural language processing. The idea of a bidirectional LSTM is that we not only want to remember what we read reading forward in the sentence, but it's also nice to be able to see where we are in the sentence the other direction. So for example, this sentence right here, the dog chased the blah, and this letter's blurred. Is he chasing a cat or a car? Could be either one, right? Well, if you read the rest of the sentence, it's very obvious that it's a cat running up a tree. It's not a car running up a tree, right? So bidirectional LSTMs read the input from both directions and can use that memory very effectively. So again, that can be extremely effective. And it's also very easy to take this very sophisticated type of approach and integrate it into TensorFlow. So here, for example, is the entire network to do bidirectional LSTM analysis on the previously mentioned IMDb movie database. It's kind of redundant, right? The IMDb movie review site has a bunch of reviews in there, and you can do sentiment analysis, see if these are thumbs up or thumbs down kind of reviews. And here's the entire network to do this pretty effectively. And it's pretty much, it's a bidirectional LSTM, and you can see how easy it is to integrate that in. You are specifying how many neurons you have, but otherwise TensorFlow is taking care of the rest of it. We got a dense layer at the end with some dropout, but I think you can understand all of this, except maybe actually this first layer, which is the embedding. When you're doing language processing, you need some way to represent the words typically. You don't just feed a bunch of letters into your network. It's not a very good head start for the network. Instead, you typically want to embed the words into some kind of encoding. And the simplest way might be if you had 1,000 words in your vocabulary, you might just make 1,000 inputs to the neurons, each one representing a word, a vector that's got 1,000 one-hot entries in it for the words, something simple-minded like that. But it turns out that a much more powerful way to represent words is instead to use a word embedding, where you might take your 1,000 words and try to come up with a vector with, say, 64 entries in it. So we want to take our 1,000 words, which are technically a 1,000-dimensional space, we want to reduce it to a 64-dimensional vector where somehow we capture all of the 1,000-word vocabulary with 64 entries in that vector. So we're actually doing a dimensionality reduction there to do that. It's a separate topic and one of you that you should investigate and dive further into if you're doing this kind of stuff, this kind of work, semantic analysis, or any kind of natural language processing. But at any rate, word embeddings is taken care of by us here with TensorFlow in a very, very straightforward way. It'll take and encode our vocabulary of whatever size. I think this is probably 1,000 or so words here into a 64-dimensional vector. So once again, like I said, this dimensionality reduction keeps coming back again and again in machine learning. Now, once we've got these layers, And covered now at this point, you've got the top 4 or 5 really most powerful, or 6 layers. Once you've got these layers, people have been building on the bigger and bigger architectures. And as a matter of fact, today, people pretty much research just basically can almost start with the big block of architecture and add them into others. So we've looked at AlexNet, and we've looked at, and I've mentioned to you some very, very deep residual networks like Google and Inception network, very deep, where you just have very simple layers. But today, people will often take and combine entire networks of multiple layers. So faster RCNN is a recurrent CNN network. It's got some pieces to it that you'd recognize all the pieces of, that's very successful at doing what it's doing. You can combine multiple copies of that together to do slightly different tasks, some region bounding, some segmentation. Anyway, you can combine them together into another bigger, faster, better network called Mask RCNN. And Mask RCNN is a very, very good network at doing, we can see here, an awful lot of analysis on an image to where it's able to not only recognize an object like a knife, tell us the certainty with which it recognizes that knife, 83% certainty, but also give us a bounding box on that knife, and even segment it out of the picture, label the pixels that are just the knife, or the pixels that are just the glass or the chair. So, and this is done by different components that are doing different parts of what's going on here. Finding some of them classify and bound the region and other pieces. Anyway, if you read the paper on Mask RCNN, you can see they basically started out with other networks that were deserving of their own papers and discussions and applications, and started stringing them together. So today we're building bigger and bigger blocks, putting things together. And again, TensorFlow makes that very easy to do. We can also take some very different paradigm, conceptually, conceptual approaches to what we're doing by combining these networks that otherwise are pretty simple and straightforward. And a class of a different paradigm, a different way of attacking problems is a generative adversarial network. This has become quite well known for a lot of game things, as well as for solving games, video game solvers, things like that, as well as generating a lot of artificial images. I'll show you a couple applications of this. But let's say that we want to use it to generate artificial pictures, new pictures of cats and dogs. Cats. We want to make something that makes pictures of cats, paints pictures of cats, essentially, photorealistic pictures of cats, cats that don't exist anywhere in the real world. Well, how could we do this with a GAN? What we can do is we can take a network and we can train it to recognize cats. So we take a bunch of cat pictures and we train a network to recognize cats. We know exactly how to do that, right? You could sit down and start typing in the TensorFlow code to recognize cats right now. That's nothing interesting to us. We're masters at cat recognition, right? Well, what if we make a network that generates cats? It's very bad at first. We just give it some input, some noise input, and it just generates a cat. And by generating a cat, it doesn't know how to generate cat images right now. So it generates some horrible, nasty, noisy picture. It doesn't look like a cat at all. And we feed this into our network that's good at recognizing cats. It's going to say this isn't a cat at all. It's going to recognize this isn't a cat. It's going to say the probability this is a cat is 0. And so it's rejecting this as a cat. Well, that actually is some feedback that we can use into this network that's painting cat pictures, or trying to learn to paint cat pictures. And it's going to, at first randomly and in a very stumbling fashion, learn to make things that look a little bit more like a cat. Okay, well, based upon this feedback here, that this thing looks a little bit more like a cat, has a slightly higher probability of a cat, it can improve itself. And eventually, it's going to start drawing cats to the point where one of its cats even slips through and fools this network. So this network might actually get fooled by one of these cats, and it gets fooled. Well, it can use that as feedback to improve itself. So now this network can say, okay, I'm going to get better and better at recognizing fake cats. And it starts to recognize these fake cats. Well, based upon that, this network down here has to do a better job of generating fake cats. It says, hey, this thing recognized fake. I got to do a better job, change the way I'm drawing my cats. So it gets better at drawing fake cats. This network gets better at recognizing fake cats. And the two of them together in this feedback loop end up being able to generate some really nice pictures of cats, of photorealistic cats. So it becomes a generative network capable of generating new things because of this adversarial approach. So again, these are pieces that we understand at a low level, but you're combining them together in a different kind of way and getting a very, very different kind of result. So GAN networks are a whole different class of interesting work. I'll present one here that uses extremely simple layers that that we've used so far to do something that is drastically different from anything that we've done so far, which is autoencoders. That we'll see how they do deepfakes. Deepfakes has become very popular and somewhat troubling, but important area of neural nets and artificial intelligence. And an autoencoder does what sounds like at first a really simple and pointless task of just generating the same output that it gets on the input side. It just takes the input and generates the same output. So if it gets this picture of this woman right here, this is the woman that we get on the output side. This woman here is the woman we get on the output side. This, again, not only sounds pointless, but if we just do it in this fashion here, all this network learns is pretty much just the identity. It just passes everything through. This is dumb. But what if we take and we try to reduce the dimensionality? So our dimensionality reduction badge is showing up here again. And how can we do that? Well, we learned early, one of the first things we learned about neural nets is the dimensionality that it's working within is the width of the network. So what if we choke down the network width in the middle of our autoencoder so that it's forced into a reduced dimension here? So we're forcing it to do dimensionality reduction, and it's trying to take and reproduce the input on the output side. What's going to happen is, well, we can call this input side where it's choking down the dimensionality of the encoder. We call this output side the decoder, where it's trying to reproduce these images, and it's not going to succeed 100% now. It's just going to come up with a similar image, we hope. And we can now call this middle section here, where it's forced to work in a reduced dimensionality, we can call this where we're controlling latent features. So again, from our recommender system earlier, right, we had these latent features where we said we're representing movie viewers by this reduced representation. In this case, we need to learn to represent these images by a reduced representation. And in human terms, we can think of these latent features as the kind of the police description of somebody, right? So we can say, this is female, long blonde hair, not smiling, brown eyes, right? We can represent this picture by this reduced representation. And based on a police sketch, we could hope to represent over here, you know, the best possible representation, given that we're forced to be lossy, we're forced down dimensionality. So forcing this encoder and this decoder to learn how to deal with these latent features, this reduced representation, this reduced dimensionality is going to, well, at first, what's the point of that? Well, it's going to give us a couple of interesting things. The first application of which would be the deepfake generator we're going to see. But there's some other applications we won't have time to drill into, which are also powerful, where if we control this latent space in here, so instead of just letting it do whatever it wants, whatever it needs to learn, we can also try to constrain that latent space. We can try to control the distribution of that latent space, and that this becomes a variational autoencoder. Variational autoencoders are nifty because the latent space, since we're controlling the way it's represented, might actually give us some dials, some human understandable. I said a big quest is to get this human understandable latent space. We didn't have it with our movie recommender system. We won't get it here by default, but with the variational autoencoder, where we try to control what that latent space looks like, you know, the kind of the standard deviation that's allowed for each one of those neurons in the middle, we can control it. We might actually end up in that latent space with some dials that control our police description. We might actually end up with one of them being hair color, one of them being facial expression. We might actually end up with dials where we can say, I want to generate a picture of a smiling man wearing glasses with a mustache. And that indeed is an application that exists. I think it's the last one I'll talk about here, based on variational autoencoders. But at the moment, we're talking about deepfake training. How does that work? Well, let's say we've trained this encoder, part of this, on some video from Alice, a bunch of video clips from Alice. So it learns a bunch of different faces from Alice. And we have an Alice decoder. Okay, so this is just the encoder decoder, same thing we've been talking about. So it learns how to compress Alice down to her police description, as it were, and to decompress it into a faithful representation of Alice. Okay, what if we do the same thing with Bob? So we get some video from Bob, and we train an encoder and a decoder with Bob. Okay, so we got these two video and encoders. Only thing is, we're going to use the same encoder for both of these steps. We're going to force this encoder to learn how to reduce for both Alice and Bob the representation down. So when it says smiling, you know, looking to the left, it's learning how to do that for both Alice and Bob. Okay, now this is where the magic of deepfakes comes in. What if we take that encoder and we feed it in Alice, but we use the decoder that we trained on Bob? Now we have a way for Alice to puppet Bob, for Alice basically to be talking and moving and saying stuff, and Bob's face is going to be the one that shows up reflecting those expressions. So this is how deepfakes work. is that we've got an encoder trained with one thing and a decoder trained with something else. And indeed, this can be very effective. So here's a demo. I won't actually activate, but you can feel free to go. It's embedded here, but I won't activate it. You can feel free to do it. And it's where it's a Chinese app. You can go to the site, then you can stick in your picture, a short video clip from you, from just a photo, not even a video clip. You can stick in your photo, and you will appear as the face in a bunch of Leonardo DiCaprio scenes from different movies. And it's quite effective for a simple little web app that takes just one photo. And it's an example. Oh, I inadvertently ran it right there. But if you run it yourself, you can see it's got a lot of power to it. And like I said, this is rather frightening and concerning from the societal perspective. It shows you how easy it is to generate deep fakes, to generate fake content that's photorealistic. But that's how it's done. It's done with the simple techniques that you already understand with neural networks layers and the concept of dimensionality reduction. But that also raises the concept for us, I mentioned, of being able to generate stuff from scratch. Both our GAN earlier that I talked about, as well as this, can actually create new content. And that is a whole different type of approach in thinking about the problem, because in our higher dimensional space, we talked about yesterday, the central hypothesis of machine learning is that our data lives in this higher dimensional manifold. And so we've got the surface. Well, for our discriminative work that we've done so far, we just want to know if something's a 4 or a 7. All we need to learn is how to separate those two places in space. We need to learn where in the manifold the 4s live and the 7s live just by dividing lines between them. But if we can actually refine that down, the harder problem of learning where exactly on the space they live and how they're distributed over that. So we know that the 7s actually live in this kind of area of our manifold and the 4s are over here. Then we can actually create new data. We can go to this point in space right here and say, what lives there? What if I spit this piece out here? I've got a new 7 that nobody ever drew by hand. I'm creating new 7s because I understand the general distribution of 7s in space. So we capture, not only the conditional probability in this case, but you have to understand the joint probability is the way of saying we understand the actual distribution of these in space. Not just, is this X given what this input, is this the output, but instead how the two relate to each other. And it's a harder problem to solve, but it allows you to be generative. And so that's a whole class of problems and useful things to do. Okay, and if so far we've had an awful lot of hand waving in these discussions and an awful lot of me saying, hey, if you want to figure out how to pick this hyperparameter or how to divide things up or where to start with these, you just got to go out and look at what people were doing. Well, I'm not misrepresenting the state of the art. This is the reality. And as a matter of fact, Jan LeCun, who's kind of a godfather of deep learning, certainly one of them, maybe the foremost in terms of he really through the 80s, when people thought that this stuff was limited in its applicability, really kept making advances, and certainly through the 90s. So when stuff exploded in the early 2000s, he was there on the scene with an awful lot of algorithms and ideas and knowledge. And this is his view. He calls it a theoretician's nightmare. And I think that sums up things pretty well, because traditionally in computer science and probability and statistics, we like to have, very mathematically precise ways of describing the behavior of the things we're working with, convergence criteria and whatnot. And we don't have that here. Instead, we have a lot of these black boxes with crazy ideas like dropout going on. They make the analysis very hard. At the heart of this, a theoretician might say that our loss functions are non-convex, right? We looked at how we're solving our problem with our stochastic gradient descent, and we're trying to minimize the error. And I told you we're going to give up on ever really trying to find the ideal zero loss or minimal loss. Instead, we're just looking for a kind of good local minimum. That gives you some idea of the kind of compromises we're making. We recognize we're dealing with some intractable problems. We're just kind of compromising and approximating things. And so you might also, like I said, notice some of the techniques we've used today are very recent. I've tried to point out some dates along the way, not just because I'm a historian, but because it gives you an idea of how rapidly evolving the field is and how immature a lot of the techniques are. We've looked at things like dropout, or the entire architecture of AlexNet and the things it brings in, like the rectified linear activation function. And these things are all, just so new, and yet they've become essential tools. So it gives you some idea how rapidly things are evolving. And there's a lot of different perspectives on this. Chris Vola, his blog, has some nice perspectives on this. My own observation, I offer you humbly as somebody coming from a science background, is that deep learning at the moment to me looks an awful lot like late 19th century chemistry at the end of the 19th century, chemistry had a very poor theoretical foundation. Quantum physics didn't really exist, so quantum chemistry and understanding at the quantum level didn't even exist. We barely were filling out the periodic table, and yet chemists were able to still do a lot of great work. A lot of our modern industrial era and our lifestyle is built on chemistry that was discovered and pioneered and even industrialized in the late 1900s. So they were able to do great work. But without the theoretical underpinnings being solid, a lot of their work was done through lab work and a lot more perspiration than inspiration. And I think that's where we are with a lot of deep learning right now, is that we don't have the theoretical understanding. We may not have anytime soon that allows us to sit down and design a network on paper and say, this is going to be great at this task. So instead, you get to spend a lot of time adapting and evolving existing work and searching for hyperparameters to make great breakthroughs. Now, the good side of that, though, is that there are so many great breakthroughs to be done that it's worth it. We're still at the point where people can come up with lots of fascinating new, and big jumps over what previously existed. So this kind of thing right here, example we looked at right here, is a very good example of how inference is fast and how once you do develop a network, you can deploy it on minimalistic hardware. Well, the case I had here, the reason I like this example was this was sitting out there on, like I said, some JavaScript. And all that JavaScript needed was the magic weights behind it. So somewhere somebody actually trained this, the guy, wonderful guy that did this, actually trained this so that, and that training might have taken a couple of hours to train this network. And he trained this network to find these weights to make this work really well. Actually, not a couple of hours, probably tens of minutes. So in tens of minutes, he trained this network on a GPU to do really well. But then you can upload this to your website and your crappy JavaScript can run this because all it needs to do is some matrix multiplies, and this thing will recognize digits in fractions of a second, right? Well, that is an important principle to understand, because it means that once you grind out and come up with these models, where you can deploy them is fairly unbounded. An easy way to see this is this iPhone demo I've got right here. Somebody even asked the question explicitly earlier, said, how come my phone can use these kind of deep learning and neural net techniques? And your phones, and today phones do it all the time. They're even built in for photo. So if you've got an iPhone, and I think probably most Samsung models, just the video filters and certainly the photo filters that do stuff, a lot of them are neural network based. And how can they do that? Well, it's because the inference part's very easy. It's lightweight. So they don't need a lot of specific hardware. Even though they do now have in them a lot of neural specific hardware, they don't need a whole lot. So here, for example, is a simple iPhone demo. It's even a couple years old at this point. And running on your iPhone in real time, it can do some pretty good complex recognition of objects and everything in real time. It's milliseconds for it to process these things and recognize it, because it's very easy to do the inference. And to a greater extent, this is visible on things like self-driving cars, which people are always talking about. And the reason I mention this is because there was this Tesla self-driving day they did about a year and a half ago, where they actually dived into some significant detail for those of you that are concerned about it. Usually this is kind of proprietary stuff. Companies don't want to give away their secrets, but they went into a lot of detail about a lot of how their chip that they put in cars to do self-driving works. And the reason I pointed out here is not only you can go and review that talk if you want, it's like an hour and a half talk, lots of interesting information, but more importantly, if we look at the architecture of their chip, as they describe it in that talk, there's nothing here that you don't understand now, right? Their chip in hardware is just really good at doing a lot of multiply adds, has some built-in rectified, linear, hardware to do that, polling hardware to do that. And as a result, because of this dedicated hardware, it can do 72 tera operations or trillion operations per second of this simple-minded math, which is all it needs to do the inference part. Now, back in some data center somewhere, they spend a lot of time training this stuff, and they're still working on it, trying to make it work. But at the end of the day, they deploy it on a very simple, chip that runs in your car, relatively low power, because the inference part's the easy part, and that's important to understand. Okay. As I was talking about inference, though, I treaded into the territory of hardware being specifically designed for deep learning. This is very important today. Instead of just having GPUs, which are increasingly themselves being oriented towards deep learning training, as a matter of fact, modern GPUs, a huge part of the hardware is dedicated just to doing, if you look at it, to neural nets. And not just for the neural net community, also because the gaming community that was enrolling in neural nets. There's also a lot of dedicated hardware that other people are doing to enable this stuff as well. One of the reasons dedicated hardware is so useful is not just that the matrix multiply kind of thing is nice to do in dedicated hardware, but also the precision is unusual. We're finding out the more we do neural nets, the more we're finding that low precision is actually quite useful. There's no need, high precision is useless for all the extra bytes you have to shuffle around and time it takes to calculate compared to the many more operations you can do with low precision, to the extent where even 4-bit precision is becoming a thing in deep learning. And certainly the mainstream equipment now is down to 16-bit precision kind of being the norm, or 8-bit precision. It's fixed point, mostly math. Nobody's doing actual real floating point math if they don't have to. So if you look at, say, just NVIDIA chips in modern GPUs, they have these cores built into them, these tensor cores, which specialize in doing 4x4 matrix multiplies in mixed precision. And that gives them really high performance compared to doing normal, high precision arithmetic. Google's TPUs, which they use in their cloud, their version 3 is up to 420 teraflops. Again, it's low mixed precision. Intel is rolling this stuff into their chips. As a matter of fact, in fairly generic vanilla chips that have the AVX chipset, I shouldn't say vanilla, higher end chipsets intended for scientific computing, but generically intended, they now have specific instructions targeted towards accelerating these kind of low precision operations. So everybody's going towards this neural net enabling hardware. And the reason a lot of people, I think there's a lot of room for improvement, is that biological inspiration I mentioned at the beginning of the talk still remains valid. We can see that biological neural nets still do things in different ways than we do. They use analog things. They do a lot of pruning where connections that get close to zero, just, hey, get rid of them altogether. So they have a lot of new inspiration to offer us. And the most important thing maybe to recognize, and the reason we think that there's so much to be gained from nature, is that if we look at the human brain, it uses about 20 watts. If we figure out computationally what it takes to model the human brain, we hope to do that on the latest, greatest exascale computers. And that's a term for the computers that are finally coming online this year after a decade of planning. They'll be able to do an exaflop, or 10 to the 18th, the quadrillion floating point operations per second. Those machines, we hope, will be able to somewhat model the brain in real time, at least for a crude approximation of neurons and whatnot. So it takes an exascale machine that takes at least 20 megawatts of power, and the first ones take over 30 megawatts. So it takes an excess of 20 megawatts of power to model a human brain, which takes 20 watts. Gives you some idea. There's a lot of room for improvement there. So lots and lots of information. But by the way, this idea of really going with the human brain and modeling things directly like it is called neuromorphic computing, where we start to make our electronics look directly like the human brain. IBM pioneered a lot of that for a while, but at the moment, we have, and let's see, I guess I don't have a picture of it here, but we have other companies, in particular, Cerberus, which is doing their wafer scale engine. Cerberus has a machine here at PSC, Neocortex, one of the first out there, which is so specifically oriented towards doing this kind of stuff that it has 1.2 trillion transistors. It's the biggest single circuit in the world because it's so focused on doing this. It's got 400,000 cores in it for doing this kind of linear algebra stuff. And consequently, it's incredibly, incredibly effective, orders of magnitude more effective at just doing deep learning. So we're excited to have one of these here because it's so leading edge. And it's a good example of how neuromorphic computing, starting to design this stuff more and more around just being neural net specific is the future for a lot of this. Okay, well, how about other approaches here? Because we've said this is so successful, deep learning at so many of these activities here. Is there room for anything else out there? And yesterday I kind of gave you the animation here. I guess it's not an animation anymore on this slide. Gave you the animation here of how deep learning has kind of crowded out all these other areas of traditional machine learning. Is that really the case? Is machine learning outside of neural nets stupid? Well, let's take a look. Does all the stuff as we get more and more sophisticated towards AI? Yesterday we looked at this journey here. Once we get out of the classic machine learning world, does all the AI stuff just really turn into neural nets? And the answer, I think, is, as a scientist, I like to let the data speak more than my opinion. And so one place you can go and collect data. You can read a lot of papers, I do. And so the more papers you read, the more you get the idea. No, there's still lots of room for classic machine learning, both to attack problems and certainly to offer inspiration and understanding of problems. But if you don't want to read a lot of papers, one quick way you can go to Kaggle, which I mentioned you already. You can go and see what are people doing with these competitions, both the big bucks ones as well as lots of other ones, which are based on, for pride. And if we go there and look, we'll see, well, there's an awful lot of success, certainly, with neural net approaches. So they're absolutely very good at a lot of these problems. However, at the moment, you might see this thing called XGBoost winning an awful lot of competitions and people using it for an awful lot. And what is XGBoost? It's a tree-based approach to machine learning, which is an old school classic machine learning approach with its latest kind of iterations here. And so trees are a very understandable approach to classic machine learning. I'm going to give you the quick 5-minute introduction to XGBoost and trees, just because it'll give you some idea of, a very, very popular approach that's very different from deep learning that's used, again, at Kaggle. That's where I got the idea of presenting slides. I went to Kaggle. I'm like, wow, XGBoost really seems to be popular these days. I'll give you a reason why it's so popular, but at any rate, let me explain what it is first. So trees in machine learning go back a long way, and there are a lot of variations of them. Many variations of them. And the idea is that we can try to develop, we want to develop a decision tree that when we throw the data at it can come up with some answers. So for example, if the data we threw at it is a bunch of demographic data for people, car buyers, and the answer we want is how likely are they to buy a certain car model. So it's kind of a regression model here to decide where we want to send our promotions, say, where do we want to send our coupons or ads for car buyers. So the decision trees we'd work out might be things like this. What's somebody's age for this particular model of car, we're trying to target? So what's their age? Are they, older than 40? Yes, then we want to go this way. What's their income? Is it more than 80? We want to go this way. And after we go down these trees, we can say, here's the factor that's going to influence how much they're going to want to buy this particular car model. And so we have factors that say they're more likely or less likely to buy a car model. And we can come to these by going down these decision trees that we've, somehow figured out the right values. We've trained the tree, and this is how it's going to spit out the right results. And this is nice. Trees are wonderful. People like trees because they are understood well from decades of research, and they're also nonlinear. So they have this nice characteristic. They're one of the few areas where we understand them and we work well with them mathematically, and they're still very nonlinear. You can see they're nonlinear because anytime you have kind of a yes-no thing, anytime that's a clue something's nonlinear. So immediately a kind of distinguishing feature. Any yes, no's, any conditionals in your code, anytime you write a code that's got an if then in it, you're firmly in the world of nonlinear behavior. So this is a nice nonlinear algorithm, but still kind of well characterized and understood. And we can try to improve this by having more trees that have more factors. So we can have another tree here that maybe includes gender. And this is a factor maybe that has an influence on purchasing desirability. And each one of these tree leaves contributes some factor, good or bad, towards whether this is a potential car buyer. So trees are very intuitive. And the way gradient boosted trees work is we keep adding more and more trees into the mix with either more factors or more refinement on the given factors, combinations that we have. And every time we add more trees, we're getting lower and lower error. They're getting better and better at predicting stuff. So we take the factors from one tree, but then we add it in that second tree with gender. We can add in more and more trees with more and more factors, including the factors from the first trees, but in different ways and refinements. And every time we add trees, we refine what we're doing. They're called gradient boosted here because we want to find out how much to boost each tree, how much each tree is going to add and contribute in as we go along. So we're using a gradient here. It's a very different gradient than the stochastic gradient descent. They're totally unrelated. It confuses a lot of people. They're totally different gradients here, totally different context for gradient. So remember this problem right here that we had with deep learning, and we said deep learning is good at attacking these kind of problems because it'll move it into 3 dimensions and punch the middle up, blah, blah, blah. Well, trees can attack these kind of problems too, because with trees, we can start saying our if, yes, no statements. If this variable is greater than this, but less than this, and the other variable is greater than this, but less than this, then hey, it's in this square. We think it's this category. And if we want to be more refined, we can have more trees. So our deeper depth in our trees. We can say if it's less than 0.5, but also greater than this, but also less than this, and this variable is less than this. So you can see we can basically chip away at the corners of our square with if-then statements to the point where we can get very refined results and say, hey, with a tree, we can only select the data that's in here. So trees with their nonlinear approach can be very effective with data sets. So that's why XGBoost is good. We can see this in action. Here's a wonderful, wonderful real-time demo of this in action. Here we've got a data set, and we can select different data sets, by the way, at this site. So I like this site a lot. Here's a data set of kind of spiralish data here, and we can see where XGBoost can go in and with trees, iteratively, these are the different generations of trees, get better and better at figuring out what the blue versus the orange data points are in the distribution. And you can influence the tree depth. These are the hyperparameters for XGBoost, the tree depth, the learning rate, the number of trees. We can, do all of this, and you can see it in real time. So this is pretty nifty. It's a great way if you want to understand gradient boosted trees. So I suggest that those of you that are interested in algorithm, go there and try the various hyperparameters out in real time. If you want to see the original paper, so the XGBoost variant. So trees are a classic machine learning algorithm. Gradient boosted trees go back a long way. XGBoost, this particular implementation, is where people are excited now because it seems to have really good performance. You can read the paper on XGBoost in particular here. You can play around with it on this website. You can get to see a video on it here if you want. But at the end of the day, XGBoost, the particular implementation, has really generated a lot of excitement because it works so well in general cases. It parallelizes. Again, parallelization is incredibly important. XGBoost is built around parallelizing well from the ground up. Very important, gives you great performance. It does a lot of really clever optimization things, uses clever cache optimization, works well with missing data. If you have some of your customers, you don't know their gender, you don't know their income, how do I deal with data points like that? Well, these kind of, gradient boosted, XGBoost deals well with that. There's ways you can make the trees deal with it, and gradient boost has that built in well. So you can grab this, the scikit-learn versions out there. There's a Spark version, since you know Spark now. Lots of versions out there. TensorFlow has a boosted tree, but it's not the XGBoost implementation, which people really seem to love. So the implementations are out there. I think that it's most popular. I don't just think this, I'm almost certain. It's most popular with people because it works well with generic hyperparameters. So to get things off the ground, if you just want to jump into a Kaggle.com challenge, it works kind of well. Just with the default hyperparameters, and you can play around with a few hyperparameters and try to get it to work better. The hyperparameter search effort is relatively low for this, which is another way of saying it's probably also not going to be the final best result. If you actually want to find the best result for a real serious problem, if you're after $100,000, it's probably not going to be XGBoost. It might be some other approach that takes a lot more effort. But if you just want to be competitive and take a shot at a problem, XGBoost might be a reasonable solution. With default hyperparameters, you don't have to screw around with a whole lot to get some decent performance. That's the number one reason XGBoost is popular at the moment. But anyway, it gives you an idea. There's a universe of tools out there you can use. I've already given you some examples from scikit-learn, a couple of things yesterday with clustering. We looked at digits. So scikit-learn, for those of you that are interested in some of these more classical machine learning techniques, is a nice toolkit that's got a bunch of pieces in it. So you now have a toolbox. You got a bunch of pieces I've introduced you to. In particular, TensorFlow, we spent a lot of time with. PyTorch, like I said, is the number one alternative. I hope I've, at least with one example, convinced you it's not dramatically different these days. The divergence between the two isn't so great. So if you get forced into a project where they're using PyTorch or whatever, you're not going to be lost. You'll pick it up quickly, or vice versa. A lot of these other things have been, Spark and scikit-learn, we've talked about a whole lot. These other ones have kind of been absorbed or disappeared into insignificance. Caffe got rolled into PyTorch. Keras is now really used via TensorFlow. So you've really seen most of the big important tools. Some other things that we didn't talk about, though, approaches to stuff are important in machine learning in the field. Like, for example, with digits, we did classification, but we could also have tried to find the digits or detected if there are any digits or found the pixels for the digits. If we've got a toll booth, automated toll booth on a highway that just finds license plates when they zip by, that's what they use around here anymore, automated toll booths. There's no collectors, just spots your license plate, sends you a bill kind of thing. That kind of application, you might be more interested in, refining what you've done. So we couldn't go into all these refinements. We don't have the time for it. There's also different ways of looking at what you're learning. We talked mostly about supervised learning with our digits. We had labeled data and we looked at it. That's how you learned colors. Your parents told you that's red. And when you pointed at a fire truck and said blue, they said, no, that's red. And that's how you learned what red is with supervised learning. So what we've been doing with our image recognition, and that applies to lots of other important areas. It requires labeled data, which means it's expensive, but augmenting can help. But there's also other ways of looking at learning. Reinforcement learning, which is how you learn to walk. You stumbled around, you eventually learn how to get your limbs on you and walk. This requires more thinking about long-term goals. Your cost function becomes a little bit harder because you've got delays between your action and reward. But this is an important category of stuff. It's how AlphaGo and robot motion and video game learners learn to work. They're basically interacting with the data, not just looking at it statically. Unsupervised learning, which is maybe how people learn to see it, because when you're born, your neurons are disorganized. How did they self-organize so that you can actually see? Well, that kind of self-organizing from nothing is an important part of machine learning as well. We actually did that with our clustering and our recommender. With clustering, we learned something from a data set with no labels, with nothing. We found latent effects from our recommender. So unsupervised learning is a big area as well. It's nice because you have unlabeled data, which is obviously a lot of times easier to get than labeled data. So all of these are done with and without deep learning, and deep learning has absolutely moved to the forefront of all of these. I'll leave off with a couple of, because we are running short on time here. Somehow we lost all that time we made up. I'll leave off with a couple of really kind of leading edge things. AI is now being used in the sciences for a lot of simulation-based stuff that seemed previously impossible. For example, not too long ago, as deep learning was really taking off and gaining traction, I had a very renowned numerical methods person I know and respect greatly say to me, I don't need a neural net to rediscover conservation of energy. In other words, neural nets are trying to discover stuff from scratch. They're never going to compete with a science code where we build in all these conservation laws and we build in the physics from scratch. And that sounded reasonable to me. As a matter of fact, I repeated that sentiment to say, well, these are some of the limitations on deep learning. And then sure enough, some papers have come out early on. This is one from just a couple of years ago, where people started to find out that machine learning deep learning in particular, could begin to see, in this case, chaotic fluid flow, flame front propagation here, started to become good at predicting stuff that really was very surprising because it's fundamental physical laws, a priori kind of fluid dynamics, and deep learning learned it. Today, it's no longer that amazing. Well, it's no longer news that that's the case, but amazing breakthroughs happen. This year's supercomputing prize, the Gordon Bell Prize, was awarded to an application that runs on Summit supercomputer very efficiently and does molecular dynamics, understands molecular folding, which at the lowest level is very, very much physics, right? And it's learned how to do molecular folding, molecular dynamics using neural nets as part of the chain. So it does some fundamental physics, but it also does neural nets. And here's the kind of the architecture going on in the different pieces. And it allows them to do things they couldn't consider doing. The length and the trajectories over, with the precision over a period of time, which is really kind of the measurement of merit with molecular dynamics, they couldn't consider doing without neural nets. That's a very drastic change in the field. 10 years ago, how do neural nets apply to molecular dynamics? Not at all. They have no relationship. Now, the best molecular dynamics simulations have neural nets embedded in them. Not only that, you can try this yourself. That's how much this is becoming into the sciences. Here, I'll give you an example from the NVIDIA GPU bootcamp that's very approachable. You can grab this off GitHub, where you can do simulated flow lines, fluid dynamics. You can find laminar fluid dynamics you can do using convolutional neural nets with a residual neural network. They have a couple of approaches to it. You can download and understand this example yourself. So it's fluid dynamics done with neural nets, very fundamental science. So anyway, I have some demos here that we don't have time for, but they're there for you to peruse anyway. Video game ray tracing, as well as some style versus content kind of web demos that give you an idea of the low level and high level content that filters can learn and how you can mix them up to get applications where you can take a photograph and it'll make a painting in that style from it. So lots of interesting stuff that you should now be able to understand based on what you're doing. If we had a third day, which we do not, we're even running out of time here today. We're gonna wrap it up right now. If we had a third day, then we could go into some of these architectures. We definitely pull some of them apart and look at the specifics using TensorFlow, but we don't. I will tell you though that if we looked at some of these papers and very leading edge advanced things, I can't help but highlight for you. And here's an interesting application that generates faces and things from scratch using GANs. These people don't exist. These cars don't exist. These bedroom scenes don't exist. It's all from scratch. We could pull this application apart with what we've talked about so far, and we dive into it with a third day. But the most important thing is, if you look at the actual paper where they did this, you'll see an awful lot of it concerns their hyperparameter search, how to find the right hyperparameters to make this work more than anything. So with that, I will officially conclude the day.